Hi everyone, my name is Juan, and today I'm very excited to present to you part of the research that I'm currently doing in my PhD, which is this high throughput calculation of approximate vibrational spectra, prioritizing potential molecular detections. So the detection of molecules in outer space is particularly appealing when trying to answer questions related to how life began. But the problem is that in order to detect these molecules in outer space, we need very high quality spectroscopic data for these molecules that we often obtain from very time-consuming procedures, both theoretically and experimentally. So here I want to present a different approach where instead of doing low throughput, high quality spectroscopic data for one or a couple of molecules, we do high throughput, approximate data for hundreds to thousands of molecules simultaneously using computational quantum chemistry. Of course, this data won't be able to allow molecular detections in space because the quality is not as good, but it has other applications that are worth discussing. For this project, we're working with a data set that contains more than 16,000 molecules thought to be potential biosignatures. So basically molecules that might indicate the presence of past or present life on a given planet. And these are mostly small to medium sized molecules, as we can see here in this histogram, where most of the molecules have a total of 10 atoms in total, including hydrogen. So of course we have these 16,000 molecules, so we don't want to perform our calculations manually. So we have sort of like developed this highly automated approach where we have a molecule identifier for each molecule from where we generate initial geometries and then run quantum chemistry calculations that provide us with the spectroscopic data needed that we want. So different applications with this data, but in this poster, I want to focus particularly on two applications. So the first one is that we can use this data to disentangle the spectral congestion. So in this figure, we have the vibrational spectrum for 4 potential biosignatures. And what we can see is that, say that we're looking for NO2, and we find that we observe a frequency at 1300 wave numbers. And we can think that that might be NO2, but in this figure, we can see that there are other 3 potential biosignatures that also have a frequency that fall within the same spectral window. And in fact, from our data set, there are other 652 molecules that also have a frequency there. So we can use this data to recognize potential misassignments in molecular spectra. The other application of this data is that we can identify the strongest absorbers in a given molecular group, depending on the intensity of their vibrational frequencies. So for example, here in this table, we have 7 phosphorus-bearing molecules that are of relevance in terrestrial atmospheres. And we can see that just from the strongest intensity in each molecule, the one in the bottom seems the one to be more likely to be detected. Of course, more studies need to be performed here because we need to analyze the physical and chemical conditions present in the observation source. But this is definitely an excellent starting point for sort of like trying to address these questions. Future directions in this work involves calculating data for conformers, including rotational spectra, because these are particularly important when identifying molecules in the interstellar medium. We can also use this data to train machine learning models for molecular detectability or to calculate vibrational spectra without using quantum chemistry. But I also encourage you to think about like what other applications you think this data may have, and please let me know because we're more than happy to collaborate in this regard. I just want to finalize saying that if you scan this QR code, it will take you to a related publication with we outlining this approach for a particular group of molecules, so phosphorus-bearing molecules. And yeah, so I'm more than happy to take any questions, and thank you.